This conference will now be recorded.
Yes, good morning everyone. Online, whether it's audible.
Yes, sir. Hello.
Yes, good morning everyone. Online, whether it's audible.
Yes,
Good morning,
audible.
sir.
Good morning,
Yes,
sir.
sir. Good morning, sir.
Yes, sir. Just 2 minutes. So today we are here to discuss about physical design demo session. Right. So all the technical queries and technical doubts will be handled by me, and I am Deepak. I am the trainer of maintainer of physical design in VLSI group. So first thing is physical design, right? So why we are using this physical design? Then we will discuss what we do in physical design. But why? Why physical design? Anyone is having idea why physical design? See, physical design, to understand why physical design, right? So physical design is mainly used to design an IC. This is called as IC. Everyone knows this, right? IC means what? Integrated circuit. So physical design mainly used to design an IC. For that purpose, we use physical design. So while designing an IC, right? When we want to design an IC, so who is going to design an IC or fabricate IC? So fabrication of IC takes place in foundry. Foundry is going to foundry is going to fabricate. IC fabrication happens in what? Foundry, right? Fabrication of IC happens in foundry. And what is foundry? What is foundry? Foundry is place where IC is fabricated. See, IC fabrication happens in nanoscale. In real scale, what you see is millimeter or centimeter or millimeter. But IC fabrication happens in nanoscale, 10 to the power of -9. Even those transistors we cannot see through our eyes. Only through complex microscopes, we can see the transistors. So when IC has to be fabricated in foundry, foundry requires huge investment. And even fabrication of IC requires huge investment.
Sir, we are
So
unable to
when
see
huge
your
investment,
screen.
yes, now it is visible.
Yes,
Yes.
yes, it's visible.
Yes, sir. Foundry is a place where we fabricate ICs. Right? So we are going to fabricate IC only in foundry, and foundry requires huge investment. So we are not in the fabrication. We are not in the fabrication role, but we are in designing an IC. Right? Where we are in what? Designing an IC. So while designing an IC, yes, please tell me. Any doubts you have? So I muted everyone. If you have any doubts, right, you can unmute and you can answer. So when we want to design an IC, to understand why physical design, right, first we have to understand ASIC design flow. What you understand? You understand what ASIC design flow. What ASIC stands for? ASIC stands for application specific integrated, right, circuits. So this IC means the here we have IC, but IC for what? Specific application, it's not for generic application. See, we have other things, right, like FPGA, field programmable gate array. You can reprogram it. You can use for any application. FPGA you can reprogram every time and you can use for any application. But ASIC is nothing not like that. If I have ASIC for mobile phone applications, means I can use only for mobile phone. SoC if I have for mobile phone application means I can use only for what? Mobile phones. So application specific means the IC is specific for particular application. I cannot use for any other applications. So that is called as application specific integrated circuits. Right. So when you want to design this application specific integrated circuits for complex designs, we use ASIC design flow. We use what? ASIC design flow. So ASIC design flow starts with these steps. It has chip specification, partitioning, functional verification, RTL synthesis, design for testability. So till design for testability is called as front end, or we not so here till functional verification is front end. Then we have back end, RTL synthesis, DFT, and totally physical design. This complete thing is physical design. So this is the steps in ASIC design flow. So what does ASIC design flow has? Right? ASIC design flow has, first we start with what? Specification. So chip specification. First we start with chip specification. See, in chip specification, generally higher team is involved, like managerial team or marketing team. Right? Everyone are involved, and they will take what is the requirement of a chip from the vendor. They have a discussion, and they'll take what is the requirement of a chip from a vendor. Right? So what is the specification? Mainly they have to take is what are the functional blocks required in the chip. Functional blocks required means what type of processor they want. Whether they want a RISC processor or CISC processor, what type of processor they want. What should be the frequency of operation, estimated frequency of operation. Operating voltage. The chip should operate at what voltage? Operating voltage. So, what should be the power consumption? So, technology. What technology they are using to implement the chip? So, whether they are using 14 nanometer technology or 28 nanometer technology, like that. Technology means what? Channel length. Channel length is called as what? Technology. A transistor has channel length, right? Channel length is nothing but what? A difference distance between source and drain. That is called as channel length. So all this information, the chip architecture team and management team and marketing team and production teams, all those all the teams will come together and they'll decide what are the specification for a chip. After having a specification, so we have functional blocks, right? Like this chip requires this many functional blocks. It should be having a PCI controller module, memory controller module, RISC core module. RISC core means memory module. Sorry, processor module, memory module, like HDRAM module, peripheral control module, Ethernet control module. So all the blocks, whatever we have, we start entering into design. Right? Next is a design entry through. Right? RTL. RTL means what? Register transfer logic. So here what we do is mainly here we use Verilog or VHDL. Use Verilog or VHDL to right. We use Verilog or VHDL to enter to the design, right? To describe a design. So why we use Verilog or VHDL? Can anyone tell me? Why we are using a Verilog or VHDL to describe a design? Why not any other languages? Or why we have to use Verilog or VHDL? That programming language. Why we have to use it? Describe the behavior of the circuit. Yes, very good, right? See, any circuit, if you see, right, describing from its behavior is easy, but describing from the structure is difficult. For example, I will ask one thing, right? I will ask people one thing. Just 1 second, there is a problem with the projector. Yes. Okay. See, for example, right, if I ask you people, explain operation of, yes, it is hardware description language. Verilog or VHDL is HDL, right? HDL is a hardware description language. See, the reason for using Verilog or VHDL mainly is, right, what is the reason is we can, it's a hardware description language, but why we use any programming language, right? Hardware description language, why we use any language, programming language to implement circuits, because we can describe any circuit through its behavior. For example, you take this, right, you take the example of mux. If I ask you people to tell what is the functional what is the behavior of a mux, if I ask you people, what you do? You have select line, you have I naught, right? You have I1 signal. So if I ask you people, explain the behavior of a mux, what you will do? How you going to describe about the behavior of a mux? Everyone can describe, right? It's not so difficult. You have select line. If select line is 0, the output y, output y is going to take what? I naught. If select line is 1, output y is going to take what? I1. This is the behavior of a mux. Everyone can remember this. But instead of this, if I ask internal structure of a mux by using gates only, anyone can tell me? Few can tell. Everyone cannot tell that. But remembering the behavior is easy, but internal structure is difficult. Means understanding the behavior of circuit is easy. So what we do is the person who is designing the digital circuit, he is not worried about internal structure much. What he do is he will describe by using a program, right? Program for mux. If you take program for mux. So what is program for mux? You have, right, if you have select line, right, if s equals or s equals 1 tick binary 0, what you have to do? That is equals. If it's equal to 1 tick binary 0, what is the output? Y is nothing but equal to what? Assign, or sorry, assign I cannot use here. Assign y is equal to what? Y is equal to I naught. Else, y is equal to what? Y is equal to I1. See, very simple, right? Describing the behavior by using programming model is very simple. So we have behavioral modeling in Verilog. So we can use if statement, we can use case statement, we can use always block. So all these things we can use and we can describe any circuit very easily. Right. So by using Verilog or VHDL, describing circuit in behavior form. Is easy. So for that reason, what we do is we use Verilog or VHDL to describe a circuit. So now after RTL coding, right, this entire phase, instead of I can call this entire phase as what? RTL coding. So after RTL coding, the design is in what form? Design is in the behavioral form. Right? I can tell it's in the text form or in the behavioral form. I can tell. So design is in the behavioral form. So behavioral form information foundry can understand. The foundry is going to fabricate IC, right? Ultimately, who is going to fabricate IC? Foundry is going to fabricate IC. But this behavioral form information foundry can't understand. Alright. So after RTL coding, the design is in behavioral form. So after writing RTL coding, next we enter into functional verification. Functional verification. So what is functional verification? Verifying a functionality of design. Verifying functionality of a design is called as what? Functional verification. So to verify functionality of a design, see you have written the design. Now design is in what form? Design is in behavioral form. The behavioral form, whether it's working like a required operation or not, you have to verify it. The required operation is implemented in this or not. You have to verify. To verify that, we use what? Functional verification. So here we have to apply different test cases. Test cases means what? Different inputs. For example, here I have select line. Here I have what? I1 and I0. So different values of yes, select line I have to apply. For I0 I have to apply different values. I1 I have to apply different values, and I have to verify what is my output. If I am getting desired output, then my design is behaving exactly what is required. If I am not getting desired output, then I have some problem with the RTL coding. I have to revisit that. So what you have to do in functional verification is apply test cases. Apply test cases. So applying test cases is easy when we have small designs. If you have bigger designs, for example, if you have 64 inputs, for example, you have 3 inputs like you have A, B, C, 3 inputs. Applying test cases, different test cases. How will you apply? 0, 0, 0, 0, 0, 1, 0, 1, 0. For all this combination, you will verify what is the output. So how many combinations you have totally? 8 combinations. It is 2 power 3. For example, in a design, you have 32-bit input, 32 inputs you have. Then how many combinations you have? 2 power 32. So number of combinations increases with the number of inputs. So bigger designs, it's not easy to verify. So we have to plan the verification. We have to plan the verification. So how I can meet all the functionality issues, how I can meet it, all the functionality issues of RTL code with the minimum number of test cases. If test cases increases, what happens? The functional verification runtime will increase. 8 test cases I can do very fast, but if I have more test cases, the runtime is going to increase. So I have to plan the test cases in such a way that, right, I have less test cases, but I have to verify all the functionality issues. Like I have reset, I have to verify reset. In the reset pin, I have how the reset is working. Reset, I have to verify preset in the design. Preset signal. I have load signal. I have to verify how the load signal is working. So each and every functionality issue I have to verify with the less test cases. That is called as a functional coverage. You have to verify here functional coverage. So first you have to go for functional coverage. So see, our interest is not physical verification. Our interest is why physical design. But if you want to learn physical verification, apart from this, you have to learn what? You have to learn system Verilog. You have to learn system Verilog. See, they're entering and exiting continuously, right? See, please, students don't enter and exit continuously in the meeting. It will affect our typing a lot. So, system Verilog is very important. Then UVM is very important. You have to learn both. Universal verification modeling or methodology. So both you have to learn to become what? Functional verification engineering. Now you have done the design. You have done the design and you have done the functional verification and you felt that your design is working exactly what is the requirement. But design is in what form? BRL form. Foundry can understand that. So first step what we do is you will come one step down. Right? The behavioral form we convert into gate level form. Connection of gates. Behavioral form will convert into what? Connection of gates. See, this if statement is going to give us what? A mux, right? So each and every Verilog code, what it is inferring, right? Everything we convert into form of what? Gates. That is called as a synthesis. So next we go with synthesis. So what is synthesis? Converting RTL into gate level netlist is called as synthesis. You will convert like this. Your RTL you have, then you convert into gate level netlist like this. This RTL synthesis tool will convert into what? Gate level connections. That is called as a synthesis. So synthesis, to perform synthesis, what are the inputs required? What are the additional things you require to perform synthesis? See, synthesis I cannot
Inputs
perform
and
directly,
outputs
right? There should be some
RTL.
constraints and be some information. So first question is, yes, please tell me.
Yeah, no, sir. Continue, please.
Yes, please repeat once again what you told. Hello.
Yes, sir. Please continue. Please.
Yes, sir. Sorry. Okay. Now what I was discussing is synthesis. So convert your RTL into gate level netlist. I'll tell you what is netlist later, or I can tell what is like gate level information. So here I have what the gates and connection between the gates. So this information we get after what? Synthesis. Right. So here, so after synthesis, what we get? We will get what? We have after synthesis we have gates and connection between gates. That is called as synthesis. Now my question is here. I told that we have gate level information. Right? Now question is what gates the tool will convert. See, the synthesis is done by tool. RTL will be converted into gate list. Now this gates, who will give this information? My tool should convert into few gates, right? What gates I have to convert? That is a question. For what gates I have to convert? Yes, who will give this information to synthesis tool? So we have to give the information. So we will get a library file called as a .lib file. Right? We'll get a library file called as .lib file from a library characterization team. Right? That information we will give to the tool. In this .lib file, we have what are all the standard cells available for conversion. So what cells present in that library file, right? Ultimately, my design will convert into those cells only. For example, in my standard cell library, I have NAND gate, NOR gate, AND gate, OR gate, XOR gate, MUX, and full adder, and D flip flop. So these are the cells present in my library file. Right. So ultimately, synthesis tool will convert into this gate level information only by picking the gates from what? Only by picking the gates from library file, not from anywhere. That is called as what? Library file. See, along with the RTL, I should also give what? Library file as an input for synthesis tool. Then only my synthesis tool can perform synthesis. I have to give gate level information or standard cell information we call. Right. So inputs for synthesis is inputs for synthesis. So what are the inputs for synthesis? See, I am just covering in depth this synthesis because it is a previous step of PD. So what are the inputs for synthesis? So one is your RTL code, right? This RTL code only we have to convert into what? This RTL code only we have to convert into gate level netlist. So one is your RTL code. Next, what is important? Yes, library, standard cell library. So I can call .lib file. .lib file is nothing but your library file. So what it contains? .lib file. Information about standard cells. It contains information about standard cells. What information? Timing and power information. Means, for example, in this .lib I have AND gate. So what is the delay of AND gate? Timing means what? Delay. What's the delay of AND gate? And how much power it's going to consume? Next I have OR gate. What is the delay of OR gate? How much power it's going to consume? So this timing and power information is present in what file? .lib file. So this file we are not generating. Our synthesis team is not generating. There is a separate team called as a library characterization team. They are going to generate this. So one thing we want is RTL code. One thing is we want is what? Library file. So next one more file what we want for synthesis is right SDC file. Synopsis design constraint file. Synopsis design constraints file. So I have RTL code which is in the BRL form that has to be converted into gate level information. So gate level information I've already told that right the gate level information is present in which file? Library file. In this library file I have all the gates which can be used for synthesis. Then in that file also we have what timing and power information for each and every gate. So next is only this much information is sufficient to perform synthesis? No. We should also give the constraints, right? Constraints means what? Your design should work at what frequency? So design should work at what? What frequency? Like it is called as timing constraints. And power constraints. What is ultimate power you have to map to? So you cannot do the synthesis blindly. Synthesis cannot be done blindly. So synthesis should be done to meet my frequency of clock. clock frequency. So in Synopsys design constraint file, we have different constraints, timing and power constraints. So it is timing and power information for each and every cell. In .lib we have what? Timing and power information. Information means this standard cell is going to consume this much power and is having this much delay. That is called as what? Timing and power information. Constraints means, see, my design has to work with this much frequency of clock. So my synthesis tool should convert in such a way that my design is working with this much frequency of clock. See, like I'll give you an example. Your parents are telling to go to VLSI Guru. If they don't give any constraints, right, your role is very easy. Book a cab, come here and go back. For if you don't have, even synthesis role is also very easy. Engineers are not required. But the problem arises when we have constraints. Your father tells that go to VLSI Guru only with 15 rupees and come back. Then your intelligence starts. You should reach VLSI Guru in less time and you should spend only 15 rupees. What bus you have to board? You have to plan everything. At what time you have to leave your home? You have to use Google Map and you have to verify everything. And you have to plan how to reach to VLSI Guru and how to go back. So there is a constraint, right? What is a constraint? You have to go. We have to do everything in what? Only 15 rupees. Similarly, synthesis you do synthesis, but you do in such a way that you have to meet this clock frequency of operation and you have to meet this power. That is called as what? Constraints. So here we have timing constraints. What constraints we get? Generally timing constraints. We have timing constraints and power constraints. During synthesis, we have to write this file, APC file. That is the role of engineer. According to the constraints, you have to write the file, you have to do the synthesis to meet these constraints. So what is output of synthesis? What is output of synthesis?
Gate level netlist.
Yes, output of synthesis is what? Gate level netlist. So everyone know what is gate level netlist?
Converting the Verilog code into gate level.
Yes, sir. What is gate level netlist? See, gate level netlist is nothing but it's also a Verilog code. See, this is RTL is also a Verilog code. Verilog or VHDL. Even your gate level netlist is also a Verilog or VHDL. And what is the difference between these two things? Generally, this is in what form? Generally, this is in behavioral form. This is in what? Structural form. See, this gate level netlist cannot have assigned keyword. In Verilog, you have what? Assigned keyword. Gate level netlist should not have always blocker. Gate level netlist should have only gate information and connection between gates. So I'll give you one example. You just see this example. Whatever. So I'll write an example here. Right. So this is a port. What's the port name? A. And this port is connected to N1 net. Right? You have one AND gate. Right. This is connecting to even this net name. Right. We also call it as A. Even this net name I call it as what? B. So this is A1 pin of AND gate. This is what? A2 pin of AND gate. This is Y pin. So next you have one inverter. It's connecting to what? One inverter. So this is a pin of inverter, Y pin of inverter, and this is a N1 net. Right? And this is connecting to one OR gate. One pin, A2 pin, this Y pin of OR gate. So this net is N3 net. Net means what? Net is nothing but is going to indicate connection between what? Two pins. So input and output of a cell is called as what? Input and output of a cell is called as pins. Here A is called as pin, Y is called as what? Pins. And the object which is used to connect the two pins is called as what? Net. So this is N3 and output net is here, it is like N4. This is a structural diagram. So structural diagram, first this structural diagram, if I write Verilog code, that is called as what? Netlist. The same, I can write the Verilog code here, right? Same the Verilog code I use like module. So what are all the inputs for what module? Right? Temporary. I'll give the module name as what? Temporary. And what are the inputs here? A, B, and output is output port. I'll call it as Y. What is the output port name? Y. A, B, Y are inputs and outputs. So what are inputs here? Inputs A, comma B. What is output? Right? Output is what? Y. You already know this. I need not to explain about this. Everyone knows about this. Now I have seen this AND gate. See, I can have any number of AND gates in the design. I can have 1000 AND gates in the design. When I perform synthesis, right, I can have multiple AND gates. Tool can use multiple AND gates. So to differentiate between one AND gate to another AND gate, tool will give instance name. For example, the instance name of this is U1, instance name of this is U2, instance name of this is what? U3. So identify different gates with the different names, right? We give what? Instance name. Now in the library, this AND gate name is AND. In the library, this library means what? The .lib. In .lib, this AND gate name is what? AND. Two input is a name. What is the instance name? U1. Right. First I have library name. AND 2 is what? Library name. Means in .lib AND gate is having this name. What is U1? Instance name. This is given by synthesis tool. Next I have to do port mapping. Next I have to do what? Port mapping. Port mapping means .A1. .A1 means for A1 pin what is connecting. What is connecting to A1 pin? Which net is connecting? A net. Comma. .B. Sorry, A2 pin. Right? A2 pin. Which net is connecting for A2 pin? B. Comma. .Y. Which net is connecting to Y pin? N1. Right? So this is called as port mapping. We have three things here. One is what? Library name of a cell. Next is what? Instance name. This is called as what? Port mapping. So next is the next cell. What is the next cell? Inverter. So inverter library name is like this, INV. So inverter cannot have, here 2 indicates 2 input. So AND gate I can have 2 inputs, 3 inputs, 4 inputs AND gate. But inverter is always having only 1 input. Specifying 1 is not required. In library I have not used that. Right? Because inverter always has what? 1 input and 1 output. Inverter cannot have 2 inputs. So what is the instance name? U2. Then do the port mapping. .A. For A pin what we are connecting? N1. For Y pin what we are connecting? .Y. What we are connecting? N3. Right? Y is connecting to which net? N3 net. Now I have gates information about my design. Whether I have connection information here, connecting between one gate to another gate, whether I have this information here. I have gates information, whether I have connection information. Yes, I have connection information, right? You can see here, this N1 net is output of what? AND gate. This net is output of what? Is connecting to output pin of AND gate, and the same net is connecting to what? Input pin of inverter. So the meaning is what? The output of this AND gate is input for what? Inverter. Means there is a connection. Connection is established here. So tool can understand like this. Similarly, you tell me how to write the last gate. So for the example, the library name is what? Say all these are library names. R gates, 2 input. What is the instance name? U3. Dot of A1. What is the net connected to that?
N3.
N3. Here, for example, here some net N5. N5. So comma. A2 is connecting to which net?
N5.
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 And Y is connecting to.
N4.
So
N4.
here port name and last net name should be same. Then it indicates that this net is connecting to what port. So I will not use N4 here. Instead of N4, the last net I'll call it as what? Y only.
Why?
Net and port name both are what? Same. So Y pin is connecting to what? Y pin is connecting to Y. Now end module. I have written for small module. It is not bigger module. So you understood. So here N3 is output of what? Inverter, but it is input to what? OR gate. Then clearly indicates that output of inverter is connecting to what? Input to the OR gate. There is a connection. The connection is already established here. So this is called as a gate level netlist. What is called as what? Gate level netlist. So this is the output from synthesis. So now design is in what form? Gate level. Design is in what form? Gate level. That is what I have written here. So gate, it is also a Verilog code, but it is in what form? It is in a structural form, but RTL is in the general design BRL form. So in a netlist, only what is allowed? Only this is allowed. What is that? Reference name, instance name, and port mapping. So you should not be having assign keyword. Right? You should not be having any assign keyword, or you should not be having any always block. You should not be having any if statements, case statements in the netlist. Only should be having these three things. One is what? Reference name, instance name, and port mapping. Then it is called as a genuine netlist.
Does the instance count change from synthesis to PNR?
No, the same netlist we are giving, but it can change for sure. Because in PNR we will add different cells again. So we will add different cells in the PNR stage also, but functionality should not be affected to meet some timing violations. So we will add some few cells. So instance count will change. Instance count means cell count. Yes, cell count will change in PNR. Placement and out.
Okay.
So after synthesis, right? So synthesis has a different steps again that we are not seeing now. But what is the input for synthesis? What is the role of synthesis? You understood. Next is what? DFT. Next is DFT. DFT stands for Design for Testability. So once IC is fabricated, I am telling when it is fabricated, where IC is fabricated in foundry, right? Once IC is fabricated, we have to test the IC. Whether see once when the IC is fabricated, everything will not be fabricated properly. So there is a more chance that IC may malfunction because everything is working in nanoscale and everything is a chemically driven process during fabrication. For example, I want a metal like this, right? I want to fabricate a metal like this. Metal layer are fabricated like this. See, I cannot put, so instead of writing here, I'll write here. I want to fabricate a metal layers like this. Two metal layers I have to fabricate like this. This is my intention to fabricate. See, I cannot put metal layer only in this region. So it's not at all possible in the nanoscale. See, if I tell paint in this much region, right, you can paint. But if I give very small region and if I tell you to paint in this region, whether you can do that? If I give very small region and if I tell you to paint only in this region, you can do that? No. When the region becomes very small, handling so only painting in this region becomes very difficult. Similarly, for the foundry, only to give the metal layer, only to fabricate metal layer, only in this region is very difficult. Foundry cannot do that because the size of metal layer in nanometer. It's not even in centimeter or millimeter. First, what foundry will do is foundry will fabricate metal layer for entire region. Entire region I have what? Metal layer. After that, foundry starts etching. Etching means cutting. Foundry starts etching, removing the metal layers wherever it's not required. Right? It starts etching. So etching is not like take a grinding machine and cut it. It's not like that. Etching is chemically driven process. You have to treat with the sulfuric acid or pure highly concentrated acid, and the metal melts away. It is chemically, everything is chemically driven. It is not like in the carpenter shop, or it's not like in the metal fabrication shops. We'll take a cutter and we'll cut it. Everything is what chemically driven. So while see, it is like chemically driven, and while they fabricate, right? While they fabricate these things, so there is a chance that the fabrication doesn't go fine every time. Right? The fabrication may also happen like this. So I'm telling in nanoscale. All these things you have to imagine what nanoscale. See, if I see this in centimeter scale, it is perfect like this, planar. But in nanoscale, it is not planar. It is like this. Right? The metal layer fabricated is like this. I have one more metal layer here in here. So it is fabricated like this. So by mistake, what happened here? It is shorted. Without the notice of the fabrication team or without the notice of the few people present in the foundry, the metal is shorted. Even they cannot notice that because we will be having millions together metal layers in the IC, not 1, 2. We will be having what? Millions. Millions means 10 lakhs. So they cannot see everything where it is shorted or where it is not shorted because even etching, right? When they are etching, it is also a chemically driven process. So by chance, if it is shorting like this and chips start malfunctioning, so this is called a short. So for that reason, we have to test the chip when it is fabricated. Immediately when chip is fabricated, we have to test the chip. To facilitate for the testing, right? DFT team add some extra circuit in the design. For what purpose? To facilitate that testing operation. For example, I have fabricated Ethernet module, and if I to test that Ethernet module chip, I cannot connect antennas and I cannot check there in the foundry. I cannot do that in the foundry. So if I have a transmitter and receiver chip, right, I cannot connect antennas and I cannot check whether transmitter and receiving is happening properly or not. So I cannot, I can check only transmitter and receiver receiving happening in the chip only if I implement if I embedded in the mobile phone gadgets along with antennas. But how to test a chip whether everything is fabricated or not? To facilitate that, right, the design for testability team, they add some additional logic without affecting the functionality of a chip. Functionality should not be disturbed. That is the role of DFT team. DFT team will add the logic immediately after synthesis. On the synthesis netlist, they add additional logic. Additional logic means additional cells, so that chip is easily testable after fabrication. Testing happens after fabrication, but they have to add the cells immediately after synthesis step. So these cells will allow them to test easily or to pass the test circuits easily. Right? For that reason, we use what? Design for testability. So what design for testability will do? It is used to add additional logic so that chip can be easily tested after synthesis. Say after fabrication, sorry. See, I will give a chip to you, and if I ask you to test it, what you will do? You don't know what is the chip. You don't know what test vectors you have to send inside. For test vectors, what type of response you will get? You don't know. So all these things are designed for testability team will build. So I have a design. Okay, for this design, this type of test vectors we have to pass. I have to check each and every nook and corner of the chip, right? Everything I have to test. For the testing purpose, what type of test vectors I have to send and what is the expected outcome. So all those information they will make ready. So in this process, right, we have different steps in this. One is scan chain insertion.
So adding the additional logic may increase the area of the design, right?
Yes, it will increase obviously. Area will increase, power consumption will increase, but it is necessary. Without testing, for example, I am the owner of the SOC manufacturer. Right? I'm the owner of the chip manufacturer. I'm the owner, and I have a chips, right? And if I forward these chips to the market without testing, and if chips fails to work in the market, right, I lose the market. If I'll completely lose the market because they will not trust me again. For example, I am giving my chips, right, to mobile phones, your mobile phones. So what the mobile phone manufacturer will do? What are the chips I have given? They will immediately embed in what mobile phones, and mobile phone starts malfunctioning, and end users will not trust the mobile phone company, and mobile phone company will not trust the chip manufacturer. I'll totally lose the market. See, to fabricate a chip, right? The chip fabrication owner will invest more than 500 crores to fabricate a chip to get into the market, new chip. And what will be the cost of chip when it comes to the market? Hardly 2,500 rupees. A mobile phone companies will purchase the SoC with 2,500 rupees because even they have additional things to do. They have even software to implement that, and they have to implement the what mobile this batteries, everything they have to embed it. Chip only will cost 2,500 or 3,000 rupees. That's it. So to meet that
So,
investment, 5 crores, how many chips they have to sell in the market?
so how and when the
If
area
I
will
lose
be
the
fixed?
market, right? Yes, tell me.
So how and when the area will be fixed and decided or designed?
I'll discuss about that. When the area is fixed, right? We'll discuss. See, area will be, see, what happens here is we have estimated area here, right? During specification, right? During specification, we have estimated area. What should be the estimated area of the chip? So the person who is involving in negotiation with the client will be experienced person. He will be knowing for this operation what is the maximum area we can utilize. So for example, I want like at least area of a chip is like 5 centimeters, 5 cross 5. At least I want this much. That idea I should be having in prayer. That type of persons only will be engaged in what? Negotiation with the client. So they are experienced persons. They will be having previous estimation what should be the area. Then only they can negotiate with the client. So client will tell what is the area, what is the expected area.
Okay,
So
thank
only
you.
experienced person will handle this negotiation with the client. So when I become a fresh engineer, I cannot handle, right? I should be having lot of experience. VLSI requires lot of experience to handle higher end. Lower end engineers can manage, but higher end they should be having a lot of experience. Even deciding frequency of operation, right? Frequency of operation at least you can decide only after synthesis. But at the beginning during negotiation, the experienced person can negotiate. Okay, this block I can operate with this much frequency, not lesser than this. So when you add the scan chain is nothing but all the flip-flops connected in scan, right? All the flip-flops connected in scan chain manner. Right? All the flip-flops will connect in scan chain manner like this. See, generally when we talk about RTL, register transfer logic means we have flip-flops. What is flip-flop? You have D input, you have what? Q output. In between you have what? Combinational cells like AND gate and NOR gate, and you have next flip-flop. So this type of implementation is general or normal. For this reason only it is called as what? Register transfer logic. So data is transferred from one register to another register. Flip-flop only is called as register. So this is normal, right? General functional information will be like this. So you'll connect all the from one flip-flop to another flip-flop. In between you have combo cells. This is general information what is present in the netlist. But what the DFT team will do is they will connect all the flip-flops in the scan chain manner. They will use one more pin, scan in pin. They will connect all the flip-flops in scan chain manner. This is called as what? Scan chain insertion. See, what is advantage of connecting flip-flops in scan chain manner? I can pass the test vectors to all the inputs of flip-flops, right? I can pass what? Test vectors. For example, I apply 1 here. If I apply 1 clock pulse, what happens? That 1 will come here. If I apply second clock pulse, what happens? This 1 will come. See, this 1 will not go to combo cells. This 1 will go to combo cells, but this path I have not turning on. I have turned off this. We have control for that. All those things, this DFT team has to do that. All these things. This path is not turned on. Which path is on now? This red color path is on. So 1 is present here. Immediately after first clock pulse, 1 is present here. If I apply second clock pulse, what happens? 1 will come outside. Again, the 1 is present here. If I apply third clock pulse, that 1 will come outside of third flip-flop. So to pass the test vectors inside the circuit, we connect flip-flops in what manner? Scan chain manner. So that is called as what? Scan chain insertion. In scan chain insertion, all the flip-flops are connected in scan chain manner. So now flip-flops I can use in two modes. One is functional mode, another one is what? Scan chain mode. Flip-flops has two connections. If I talk about the flip-flops, right? So you have Q pin, you have D pin, you have Q pin, you have D pin. So what is the normal path here? What is the normal path? Between Q pin to D pin, you have combo cells, right? This combo cell is what? Normal path, normal functional path.
Edge to edge.
What is scan chain? Just tell me. Yes, what is a scan chain path? This is scan chain path. So here I have one more pin called as SI pin. So when scan chain paths are enabled, your normal paths are what? Disabled. When scan chain paths are not enabled, your normal paths are enabled. So all these things your DFT team should take care. So why this scan chain insertion is done? To pass the test vectors. There is a separate course for this, DFT. Right? That is a separate team again. It's not a part of synthesis, even it's not a part of physical design. Separate team it is. Their role is to insert scan chain. Then their role is to do built-in self-test. That is done for memories. They will do built-in self-test. So then they will do ATPG. See, I'm not going to discuss about this in depth because I will lose the content of PD. Right? PD I have to discuss in depth. See, these are the different steps. It's a separate team again. ATPG means automatic test pattern generation. So these are all the things which they are going to inbuilt in our IC. So built-in self-test is mainly used to test the memories. Automatic test pattern generation means it will automatically generate a test pattern for the design. What test pattern I can use to test entire chip? To generate a test pattern. Even this logic we have to insert inside the IC. Right? So these are the different methods what we have in design for what? In design for testability. What design for testability will do? They just add some additional logic into the chip so the chip can be easily tested after fabrication. So now, but till now, the design is in what form? Yes, sir. Design is in the gate level. Even this gate level form, foundry will not understand. If I give this to foundry, foundry will not fabricate this. In foundry, generally we have chemical engineers, not the electronic engineers. Generally, I cannot tell that there are no electronics engineers, but generally, right, who are doing fabrication, chemical engineers. So next is right to convert into gate level information to into layout form or physical form is called as what? Physical design. All the gates have to convert into layout form or physical form. So what is a physical? For example, I have taken one layout here. Everyone know what is layout. I don't know how many of them you know layout. This is called as layout. Layout of an inverter. Everyone know what is inverter, right? What is inverter? CMOS inverter. So if you know, that is fine. If you don't know, we have even basic courses, right? Even we have basic, that is along with PD. So there we'll also discuss about CMOS.
Combination of PMOS and NMOS.
This is called as what? Yes, please tell me. Yes, please tell me what you told.
I just told like combination of PMOS and NMOS.
This is correct. Good. So it is like PMOS and NMOS. A combination of PMOS and NMOS is called as what? CMOS. When PMOS is on, NMOS is off. When NMOS is off, PMOS is on. For that reason, it is called as CMOS. It means complementary metal oxide semiconductor. The operation is complementary. See, in interview, they will not ask always set of questions. Even they will ask this basics also. What is full form of CMOS? Why it is called as a complementary? Complementary. Why it is called as complementary? Because when PMOS is on, NMOS is off, and NMOS is on, PMOS is off. For that reason, it is called as what? Complementary. Why it is called as metal oxide semiconductor? What is full form of MOSFET? Metal oxide semiconductor field effect transistor. Why it is called as field? Why there is a word field effect? So even these basic questions can be asked in interviews. So we have CMOS basics for that. So it is called as field effect transistor because electric field is responsible for conduction. So now foundry can understand this layout information. This is a layout. In this layout, so I don't know how many of you can understand what are the layers. This is metal layer. Blue color is what? Metal layer.
Metal layer. And input is
So this
like
is
that is one.
P plus region. Right? P plus region. This is N well. Right? PMOS is fabricated in N well. This is N well.
Input is polygon.
Ah yes, this input is polysilicon. This is polysilicon.
And below is N region.
This is like via. Right? It is a via. It is connecting between polysilicon and metal layer, both. So metal layer is present here. Metal is in present here, and it connecting to polysilicon. Via means it's connecting two different layers, polysilicon and metal layer. And it's out. So here, this is what N plus region. What is this? N plus region means NMOS. So this is called as here CMOS circuit. CMOS layout. Right? What is this totally? CMOS layout. So here, foundry can understand this layout. What a foundry can understand? Foundry can understand only this layout. This is what a foundry can understand. Now, what is physical design then? Right. The till now after synthesis, the design is in the gate level form that you have to convert into layout form, entire layout. Right. That is called as what? Physical design. So, what is next is physical design? Converting gate level netlist into physical information. Physical information is called as what? Physical design. So what are the steps in physical design? Physical design is not a one-step process. The physical design is not a one-step process. You have plenty of steps here.
Floor plan, placement,
So the steps involves, right, floor plan,
placement,
placement,
CTS,
CTS, so routing,
static time analysis,
PV,
yes, good. STA, STA stands for static timing
time
analysis.
flow, time closure,
Yes, what you told? STA only is the time closing, right? Static timing analysis.
yes sir,
physical verification,
signal routing,
So this is not part of PD. I can tell it like a sign of checks.
signal routing, sign off,
So the sign of checks. So instead of STA, I can call it as a right timing sign
Formal
off.
verification.
Timing sign off. So next it is I can call it as power sign off.
partition,
Next is right. So partition comes in the beginning. Right? So partition, you
Abbreviation.
cannot tell it is a step, right? It is like a partition. So last power sign off. After power sign off, we have physical verification. These are all the steps in physical design. CTS, I have mentioned, right? CTS is mentioned. So here, first is what partition, right? Partition full chip, right? Partition full chip into blocks. That is called as partition. So you have full chip here like this. You have full chip, right? See, doing the physical design for full chip is very difficult. Runtime will be very huge. Runtime means if I type only one command like right, place opt or clock opt, that one command will take 18 hours or 20 hours to complete. If you run for more number of cells, if I have more number of cells, it will take more time. So full chips will be having millions of gates. Millions means 10 lakhs or 15 lakh cells. So if I start doing physical design, right, 15 lakh cells, right, it is runtime is very huge. The runtime will be very huge. So what we do is, see, clock tree synthesis I have already mentioned here, CTS is clock tree synthesis. So what we do is complete full chip we divide into different blocks like this. We start differentiating into blocks. Complete full chip. This block is A block. Give to one engineer. This block is what? B block. Give to one engineer. So C block give to one engineer. D block give to one engineer. E block give to one engineer. F, right? G, H. So each and every blocks you give to one engineer. So each and every engineer will do physical design on each and every block. Right? So the person who is handling the full chip is called as a full chip designer or chip top, and person who is handling each and every block, right, is called as block level engineer. So you are all block level. So the freshers who enter into industry, they are block level engineers. So to handle the full chip, you need a lot of experience. That your role, you will get this role only after 5 years or 6 years of experience, full chip. So when each and every block, right, we do physical design, at last the full chip designer will integrate all these blocks into single chip. So this is called as what? This is called as what? Partitioning. So partitioning means what? Converting the entire block into, partitioning means converting this entire block into, sorry, entire chip into different block. This block, and this is fully full chip. Doing PD for block and PD for full chip slightly varies. It's not both are exactly same. It slightly varies. Here we have RDL routing. Here we don't have RDL routing. RDL routing is connecting for RDL bumps to the IO parts, but here we don't do that. So here we use IO parts. Here we use ports. Like that, there is a small difference between full chip level design and block level design. So as a fresher, so you will start with what? You'll start with block level physical design. It's a part of full chip. See, I need not to do always a block level. See, when we do any design, right? Block level design. So it's not that always we can integrate in the chip. See, we can create different IPs. For example, one person is creating a block. One person wants a block. So I want one block. For example, I'll take that I want a RISC core processor. I want what? RISC core processor. I want this block, RISC core processor. I want to integrate in my design. So to build this RISC core processor, I have to assign for engineers and I have to wait till he completes physical design. I have to do that. But I see that some other company has already done this physical design for RISC core processor. Block level implementation they already done. So they call this as IP, intellectual property. They've already done this. This IP is already they have done. I can directly purchase this IP from them, and I can use in my block or in my chip. Right? In this chip, I can directly purchase them. So this all the companies in this VLSI, they are not entering into fabrication. They create IPs like this, and they'll keep. Whenever any companies want this IP, they'll purchase from these companies. There are a few companies like this. Only they'll produce what IPs. So they are not involved in fabrication. They create IPs so that others can utilize this. See, the chip fabrication effort is reduced, right? Effort of chip fabrication is reduced because I am directly purchasing from some other vendor IPs and I'll integrate that and I'll send this chip for fabrication. So few companies are only involved in block level design, means that is called as IP generation. So this block level can integrate into full chip design. It is a partition of it may be partition of full chip design, or I can develop the own IPs. I can develop and I can keep it. Whenever the company wants my IP, I can sell it. So I am expert in RISC core design. I will design a different RISC core processors by reducing the power, by meeting the high frequency of operation. Everything I do for different technologies, like till 4 nanometer, I'll keep it. Then whenever the company wants, I sell it. So that is called as what? IP. So even block level design is also called as IP design. So IP can be, the block level design can be a partition block of full chip, or we can generate simply we can generate blocks, and whenever a designer wants, we can give this information. They can utilize our block in their design. We can do that. It is like your polygram mix, right? Polygram mix is already ready. You just purchase, right? Mix to your rice. Your rice is ready. Why you want to waste the time in preparing polygram mix? That has reduced the effort of many woman who is preparing the food, right? The effort of them is reduced totally. So the same thing. That is the thing, right? So IP means it is like IP and block level design both are same. So first step is what? Full chip partitioning. Partitioning means partition full chip into different blocks. full chip. Next is floor plan. Next is what? Floor plan. So floor plan involves creating a core area, and die area. Right? First, I have to create what? Core area and die area. Even for block level design and even for full chip level design, both. If you are a full chip level designer, you will create for full chip, and if you are the block level designer, you will create for what? Block level. So I have a netlist. For the block level also, the blended netlist will be given to me. For that netlist, what I do is I will estimate how much area I want to place all the cells. See, if the cell, if you take this a layout of a cell, right? What is layout of a cell? I have already shown you. This is called as what? Layout of a cell. So for this layout of a cell, we know what is a width. This width is mentioned in .lib file. Sorry, not .lib file. It is mentioned in LEF file. There is a file called as what? LEF file. So LEF file has physical layout information of a cell. What it does? Layout information of a cell. I can call it as physical information of a cell. So layout we are not creating. Layout for standard cells is already created from the layout team. They will give us in a file called as LEF file. So layout information is present in LEF file. The LEF file has what is height and width of a cell. This is width and what is height. This information is present in what? This information is present in LEF. For every cell, every standard cell, I know what is the height and width. My tool can calculate this. By calculating what is the overall, for example, this is having width 5 micrometer and height what? 5 micrometer. If I have 10 cells like this, I know what your total area requirement. So height is 5 cells means if I have 10 cells, I can place cells like this. 3, 4, right? What? 5. So I know what is the overall area requirement, total area requirement. So my tool can calculate what is the area requirement by analyzing the input files. So height and width of a cell is present in LEF file. So by calculating that, first my tool will create right core area and die area. So first you have to create a core area and die area. This is called as core area. This is die area. So first you have to create. See, I cannot create this core area and die area how much ever I want by estimating how much, what is the cell area requirement. So if for example my cell area requirement is like, just assume 100 micrometer square, this much area I want. Don't create core area only for 100 micrometer. Take some extra area because even I want to insert few cells during CTS and all. So like 20% extra area will take. What is 20% of 100 micrometer? 120. So you create core area for 120 micrometer. So like that you create what? Core area and die area. This is called as core area and outside box is called as what? Die area. So first step in floor plan is creating core area and die area. So you will study in depth in the course, right? How to create core area and die area. What are the commands? What are the different parameters governing this core area and die area? So core area and die area for the block level design, even it can be of different shapes also. Always it need not be of square shape. Even you can have different shapes. Even you can have this L shape also, like this. This is your core area, and also you have what? Die area for L shape. Even block level designer, full chip should be of rectangle shape only, but block level can be of any shape. So what shape is this? L shape. So during partition, right, my chip top for one block, during partition my chip top was a partition like this, right? Yes, my block C, yes, partition like this. So what is block C? Which shape it is? Block C, inverted L, right? If it is block C, which shape is block C? Inverted L.
Rectilinear.
So to accommodate all the blocks in the prescribed full chip area, so even my block level block shape can be even different shapes. L shape, U shape, any shape you can have. Yes, please tell me what's your doubt. Yes, please tell me.
No, I said rectilinear. That's it.
Yes, rectilinear. Yes. So that is right. That is called as creating core area and die area with the different shapes. Also, we can create how to create it. All these things we will study. Right. So this is called as what, partitioning. So after partitioning, right, next step is port placement. So inputs and outputs of a block level design is called as what, ports, and inputs and outputs of a cell is called as what, pins. You have a pin cell here, right? Standard cell. So input and output of a cell is called as what, pins. This is called as what, A1 pin. This is called as A2 pin. This is called as what, Y pin. Similarly, input and output of a block is called as what, ports. So next I have to place the ports according to full chip. So port placement then, right, done according to full chip level requirement. Right. Port placement is done according to what, full chip level requirement. So full chip level design engineer will tell where to place all input and output ports. So my full chip level design is telling place all the input ports here, right, in this region. All the input ports you place here, all the output ports you place here. Right? He's telling like this. Then I have to place accordingly. So why my full chip level designer will tell only to place a particular region? Because ultimately he is integrating, right? All these blocks, who is integrating? He is integrating. For example, right? For example, you assume that this is a F block. It is this F block, all the input ports, output of C block is going to what? F block. And the inputs of all the F block, it will be good if I place here, right? Because as soon as I get the outputs from C block, I can directly get into what? F block. And all the outputs of F block is going to what? B block. Then place all the output ports here. It will be good for you. Place all the output ports here. So immediately after the F block, all the outputs you can send to what? You can send to B block. So it will facilitate his integration very good. Correct. So based on this, right, your full chip level designer will tell that where to place the ports. So ports are simple metal layers, which will help the full chip level designer to just connect from one block to another block. So just ports. Ports are simple metal layers. So place the ports like this. So in this region, I have to place all the input ports. Start placing the ports. Correct. Ports are just what, metal layers. So here, all the output ports you place here. That is port placement. So all the signals from input ports will go to what? It will go to go into your core area, and all the outputs from core area will go to what? Output ports, correct? So the second step in floor planning is what? Port placement. That is what we have discussed here. So next step, after this, the next step is macro placement. See, few complex blocks which are already optimized. Which are already optimized. Optimized means they are the best blocks. Is called as macros. Few complex blocks which are already optimized are called as what? Macros. So if I have any macros in the design, right, I should do the macro placement. Macros are what? Complex cells which are already optimized. For example, in the design I want few SDRAM. So SDRAM, right? So I will purchase from one vendor, like SDRAM IP. I will purchase from the vendor. He has already designed and he has already optimized the SDRAM. So directly the layout of SDRAM, right? Abstract layout of the SDRAM, I am going to place in the design. This is a macro. So this macros will not be in huge count, it will be less count. If your standard cell count is in 50,000, your macros will be like 40 or 50. That's it. So first to plan and place the macros where you have to place. What are macros? Macros are complex cells, very big cells. So place the macros. Few cells which we cannot design through PD, right? Even those cells we get from analog designers. Even those are called as what? Macros. For example, PLL, phase lock loop. I want PLL to increase the clock frequency. I have 100 megahertz clock. I want to increase to what? 200 megahertz clock. Then I want PLL. So PLL I cannot get through digital design. That should be done through analog design. So who has done the PLL, right? I'll get the layout information from them and I'll place in the design. So all these are macros layout. Right? All these are macros. In this, what I have? I have layout of a macro. All these are layout of a macros. So macro placement is not so simple. You have to place a macro in such a way that you are getting enough placement, you are getting enough area to placement of standard cells. So we have to plan how to place the macros. That is called as floor plan. So macros will be of small count. So if you have 50, 60, 70 standard cells means macros will be only 50 to 60. All 60 macros, how we have to place? You have to plan. That is called as what? Macro placement. All these are macros. After macro placement, right? After macro placement, we have to go with the power planning. So power planning means why we have to do power planning? Each and every cell in the design wants VDD and VSS. VDD power and VSS. For example, if I have 60,000 cells in the design, all 60,000 cells requires what? VDD and VSS. So the problem, see, even you see the grid, or when you see your electric poles also, here and there you have transformers, right? Because your voltage will drop down because of resistance, wire resistance. For example, you take this example here, right? If you take this example, you have 1.5 volts here, right? You are taking through metal layer to a long distance, and here you are connecting to a cell. This 1.5 volts you are connecting to the cell here. whether this cell is going to get same 1.5 volts voltage. The cell will get the same 1.5 voltage. See, because this metal layer has resistance, right? When the current is flowing through this metal layer, right, it also has some resistance. Every metal layer has resistance. If metal length increases, resistance also increases. So current is flowing, right? Here you have R and current is flowing. What is I is flowing. So if I into R will result in what? Voltage drop on the metal layer. So out of 1.5 volts, 0.2 volts will drop on the metal layer. 0.2 voltage will drop on what? Metal layer. Because metal layer has resistance. So remaining 1.3 volts out of 1.5, 0.2 is a voltage drop happening on metal layer, and remaining 1.3 volts will reach to what? Standard cell. For example, I have port here. In this example only you take, right? I have a VDD port here and standard cell is present here. So what is the metal length? I have to connect from here and I have to connect from here. This much metal length. So more metal length, more IR drop. So here I have 1.5 volts VDD. In lower technology, VDD is very less. It's not 5 volts. In UG, you have studied that UG, you would have studied VDD is what? 5 volts or 12 volts. But when you go to lower technology like 28 nanometer, 14 nanometer, VDD is only 1.5 volt. So this 1.5 volt, when it reaches to the cell, right, the voltage would have become 1.2 volts. So 0.3 volt will drop on what? Will drop on this metal layer. So it will drop down. So this we call it as IR drop. What is called that? This is called as IR drop. So we have to do power planning in such a way that all cells are getting power, first of all, VDD and VSS. So with negligible IR drop should not happen like this. So for that reason, we have to start with what? Planning the power, how to distribute the power everywhere to the all cells without what? IR drop. So that is the main role of what? Power planning. Power planning is nothing but plan to connect VDD and VSS with plan to connect VDD and VSS with all cells in design with plan to connect VDD and VSS to all cells in design with the negligible IR drop. If the voltage is falling down, no issue, sir. If voltage is falling down by large amount, then the circuits starts operating in different way. So for that reason, we have to see all these things comes under floor planning. I have written here, sorry. All these things comes under what? Floor planning. So in floor planning, first step is what? Creating core and die area. Next is port placement. Ports are metal layers here, right? What are ports? Metal layers. Next is what? Macro placement. What you are placing layout of a cell here. What you are placing layout of a complex cell. In this block, inside this block, you have a layout information. So we are not drawing the layout. The layout is already drawn from the layout team. We are using that. For standard cells, we get layout in LEF form. For macros also, we get in the LEF form, layout exchange format. In that file, we have layout information. So next is, right? What's the next step? After floor plan, what's the next step? Placement.
Placement.
Place cell all standard cells in the design inside the core area is called as what? Placement. So here standard cells are not 1, 2 or 60s or 100s. We will be having in thousands. In block level design, we will be having in what? Thousands. Like 50,000, 60,000, 1 lakh. 1.5 lakhs. So all these 1.5 lakh cells we have to place inside the core area. We have to plan in such a way that how we can place them. Right? So for example, two cells are having connections. One standard cell I place here, another standard cell I place here. Whether it's a good placement, because if these two cells are communicating, how much metal length you want, right? Minimum you want this much metal length. So instead of this, right? Instead of this, what I can do is I can place the standard cell nearby only. So what is the metal length required? Very small metal length required. If metal length is more, resistance increases. If resistance increases, IR drop increases. There is electron migration effect. Cell net delay increases. If length of a wire increases, net delay. Even this metal layer also has delay. Its delay increases. So I have to plan in such a way that the cells which are communicating to each other should be placed nearby. And my timing should be met. The congestion there should be no huge congestion. All those things I have to take care. So that is called as placement. So placing all standard cells inside core area is called as placement. So we are placing all standard cells inside core area. So during placement, we have to take care. During placement, we have to take care congestion and timing. See, timing means there is setup violation, there is hold violation. That will come under STA. So setup and hold violation should not happen. So if cells are close by, nearly that will not happen. Right? Congestion means, see, all the cells should not be placed only at particular region. The cells should be spread all over the things, so that the cells can be routed easily. I can connect one cell to another cell what very easily. If cells are present only at one location, then connecting the cells become very difficult. So see that cells are spread equally to all the regions. So for example, if I place all the cells only in this region, if I place all the cells, it's not correct. Utilize all the areas, spread the cells equally, so that I can connect all the cells easily. Right? So there is a concept called as tracks. So we should get sufficient tracks to connect the standard cells. The tracks you'll understand later what is tracks when you enter into the design. Right? So while placement of standard cells, all the standard cells we have placed now. Right? Like this, standard cells are placed. All millions of standard cells are, sorry, not millions. In the block level design, we'll be having 1 lakh or 90,000, 70,000 standard cells. We are placed inside the core area. This is called as what? Placement. So during placement, what will take care? Congestion and timing. So timing means setup and hold. That you will discuss in STA part. Static timing analysis. So we'll take a break now. Right? So we'll continue after the break. So now time is 11:40. So we'll start at 11:50. 10 minutes break. We'll start at 11:50 again. See, there are few checks we have to do after CTS placement. I'll just mention the checks names. So all these checks we have to do in the tool. So it's not only about placement, right? So we have to do all the checks, all these checks. So checks are like we have to do congestion analysis. Congestion analysis. So after placement, we should do congestion analysis. Means after placing the cells, whether all cells can be routed or not. Routed means all cells can be connected or not. Whether I'm getting sufficient space for that, for connection. That is called as what? Congestion analysis. If congestion analysis is not good, then redo the placement or change the floor planning, right? Change the macro placement, redo the placement. That is not one iteration. You have to do multiple iterations till you are congestion free, right? It is a till like what? Congestion free. Congestion means verify whether you're getting sufficient space to connect all the cells by using metal layers. That is called as routing. Connecting all the cells by using metal layer is called as what? Routing. So that you have to do. So you have to do congestion analysis. After congestion analysis, you have to check max capacitance and max transition violation. So this you will study in STA, static timing analysis. What is max cap and max trans violation? So next you have to verify about setup violation. Setup violations. So if all these violations are in the limit, then only you can go for what? CTS, clock tree synthesis. If they are not in the limit, redo the placement again and again, or use some fixing methods to fix all this, right? To fix all these things. So in the placement, we will study how to fix all these things. More than doing the placement, right? Understanding how to fix is important thing. That you learn in the course, how to fix all these issues. First, you should be knowing what is this issue and how to fix it. That is what required in physical design. Everything tool only will do. Placement tool will do. CTS tool will do. Routing tool will do. But any violations are there. What is a violation? What method I have to use to fix this violation? That is a role of physical design engineer. That's it. If you develop this capability, you will become expert in physical design or VLSI. What is a problem and what is a method we have to use to fix it? So that is called as a placement checks. Checks after placement. You have to verify whether you have. So this is also setup violation. Also, you'll understand in ST. Static timing analysis. So covered along with this course. Before placement, we do STA. In the course, right? Before placement, we do what? Static timing analysis. Then we complete placement. So placement only will take one month almost to complete. It's not so easy how we tell. Fixing these issues will take a lot of time. So next is clock tree synthesis.
There are some other checks I think we have used and after placement.
Yes.
I think legality issues and unpaced checks. Unpaced cells also we have to check after the placement.
Yes, legality is not a bigger issue. All right, if at all legalized placement will fix the legality issues. If you have very less utilization, right, then only you will undergo with legality issues. That is not a bigger issue. Even that is also one of the checks. Like that, right? We have plenty of checks, but these are the major checks we have to do.
Okay.
Legalization means the cell should be placed on side rows. Cells should not overlap to each other. It's like that, you have many checks. Those are all small checks. These are the major checks what you have to complete. Why it is called small checks means generally if you use if you have proper utilization, the legality will not fail. Generally cells are legally placed. So tool will take care about that. Legalizer will take care. So to legalize the placement.
And how about this unconstrained endpoints and unclocked registers?
See, your voice is very low. So please be a little bit louder. Hello.
Yeah, I'm asking like how about this unconstrained endpoints and unclocked registers? Those needs to be checked, right?
That is called a sanity check. Right. That also, see, everything we cannot cover in the demo class. There are a lot of things to be checked before starting STA. So you have to do check timing. So check timing will report other things, but I cannot tell in the demo class all those things. So demo class is for understanding what is the physical design, why we do it. So you have plenty of checks like that. If I tell, right, even netlist only, after netlist only we have plenty of checks. In the netlist only we have plenty of checks. You don't worry about timing. You just verify about use a netlist. Netlist only have plenty of checks. So you should not be having assigned keyword. You should not be having always block. You should not be having multi-driven nets. You should not be having unconnected ports, unconnected pins. So pins are driven by constant values, zeros or ones. So if you have unconstrained inputs or unconstrained output, right? If I want to talk about that, then I have to talk about set input delay, set output delay. So all these things, if you want to do, means it will take more time. Only I am briefing out what are the major checks we do. Entire physical design I cannot teach in 3 hours. Right? Unconstrained ports means set input delay is not defined on that, or the pin is not driven from a cell. So if I tell that, no one will understand that. I can tell only major steps in the demo class. So what is a clock tree? See, that is what? That is all these things you will learn in STA. In STA, all these things you will learn. So SDC, right? I told SDC. I told only you have clock information, but timing constraints. Timing constraints, I told only the clock frequency. You don't have only clock frequency. You have set input delay, set output delay, set driving cell, set load. If this is not defined, then you will get unconstrained inputs, unconstrained outputs. So all these things you will get. So check timing command will produce all these things. So that you have to verify first. So to understand that, first you have to understand what is STA. Right? So then you'll understand all those things. So next step is after placement. The next step is clock tree synthesis. So name only tells that you are going to build a clock tree. Why it is required clock tree? Why it is required? Can anyone tell me why clock tree is required? See, clock tree synthesis means build a clock tree. Build a clock tree by using inverters and buffers. So why we have to build a clock tree? See, if I are given a task to train 50 students, right, I can do. But if I are given a task to train 1000 students, whether I can do efficiently? Because load on me is what? Very huge. So to reduce the load on clock port, right, we build what? Clock tree. So in the design after netlist, right, if you see the netlist, after netlist, you will be having a clock port. You have a clock port and you have many flip-flops. In the design, you have plenty of flip-flops. All the flip-flops has what? All the flip-flops has clock port. So from this clock port, I have to connect to all the flip-flops. So generally flip-flops count will be like 2000 or 3000 in the design. So this clock port is connecting to all the 2000 flip-flops. Like this. It's connecting to all the 2000 flip-flops. If I connect to all the 2000 flip-flops, so what is the load on this clock port? See, every flip-flop will be having its own pin capacitance. Small pin capacitance it will be having. right? It will be having pin capacitance, and you also have what net capacitance. Net also has some parasitic capacitance. Net means metal layer. Metal layer internally it has resistance and capacitance. Capacitance to ground. Right? So your metal layer is acting as a top metal layer, and your ground is acting like a bottom metal layer. In between you have air or vacuum. It's going to act like was parallel plate capacitor. So between metal layer and ground, there is what? There is a small capacitance. So you have pin capacitance. Pin capacitance means every pin of a standard cell has some small capacitance. So all this capacitance will become load capacitance to the port. Sum of all the capacitance. See, we are not connecting this capacitance. This capacitance is formed because of what? Virtue of their properties. So every flip-flop will be having pin capacitance. Even you have net capacitance. All this pin capacitance and net capacitance will become what? Will become the load capacitance. So when I call this clock is rising, when I call this clock is falling, when do we call that? The clock is rising and clock is falling. This is my clock, right? This is the clock. This is the ideal clock. If I have very huge capacitance here on this, if the capacitance is fully charged, then it's called as what? Clock is raised. If capacitance is fully discharged, then it's called as what? Clock is fallen down. This is called as rise time. The time taken by the signal to change from low to high is called as rise time, and from high to low is called as what? Fall time. So if the capacitance is very huge, if this load capacitance is very huge, my clock will take more time to rise and more time to what? Fall. So all 2000 flip-flops pin capacitance is going to form load capacitance. So my clock will take more time to rise and more time to what? Fall. So instead of clock signal, what signal I am getting? Triangle signal. Why it is I am getting triangle signal? Because of what? Huge load on the clock pin. I have huge load. So what is the intention of clock tree synthesis? Is reduce this load. What you do is what? Reduce the load by inserting what? Buffers. The same thing. What I do is I will start connecting, right? I will start forming through buffers and inverters. What I do is from the clock port, right, I use 2 buffers. From the clock port, I use what? 2 buffers. Now, what is the load on the clock pin? Pin capacitance buffer 1 and pin capacitance of what? Buffer 2. So that is a load on what? Load on the clock pin. It is very small. Earlier it was pin capacitance of all 2000 cells. Now it's only 2 cells. So 2 buffers you use. And this buffer you connect to another 2 buffers. This buffer you connect to another 2 buffers. This buffers you connect to another 2 buffers. This buffer you connect to another 2 buffers. And this buffer you connect here. So this buffer, right? This buffer you connect here. So this is the long net. What is the long? See, the net length increases, again transition time increases. Rise time and fall time is going to increase. To decrease the net length, I will use one more buffer here. Only to break what? Long net. Like it's a transformers. One more buffer you use. Long net is broken down. So transition time will not increase. Transition time will not increase. Now what you do is go and connect here. So even, right? Take this. So long net. So what you do is use one more buffer. Go and connect here. So like this, right? Build a clock tree to connect what? Build a clock tree to connect your flip-flops. So long net to connect. Use one more buffer and connect here. Here you have long net. Use one more buffer and connect here. So like this, use inverters and buffers and connect to what? All the flip-flops by inserting extra buffers. Right? So one thing is you should not use long nets. Long nets will lead to what? More transition. If more transition, clock signal will take more time to raise and more time to what? Fall. So here I have fall pulse. This fall pulse is good, no issues. But rise pulse is very small. The small on time is very small. You see here, right? On time is very small, but Off time is huge. Small on time cannot be accepted. See, there is a minimum time which is called as on time. There is a minimum time called as what? Off time. That minimum time I have to maintain. If this minimum time I have to maintain means what I should do? I should reduce this transition, right? I should reduce what? Transition. So for this reason, I cannot use any number of buffers I want in the design. See, you see here, the clock edge at this port is coming at 0 nanosecond. You just see that this is a clock which is coming at what nanosecond? 0 nanosecond. If the same clock edge, this is clock edge, to this flip-flop I call the C flip-flop. It is reaching how many nanosecond? You have delay of what? 1 buffer, delay of 2 buffer, delay of 3rd buffer, 4th buffer, 5th, 4 buffers I have, 4 buffer delay. Each buffer is having 0.1 nanosecond means, so after how many nanosecond is reaching? After 0.4 nanosecond. The same clock edge to the C flip-flop I will get after 0.4 nanosecond. So even you also have some small delay transition, small transition you have. Right? So the same clock edge what you were getting at 0 nanosecond, I am getting to this flip-flop after how many nanosecond? 0.4 nanosecond. So this is called as insertion delay. This buffer delay is called as what? Insertion delay. So my CTS tool should see that this transition is in the limit. First thing. For that reason only we are building clock tree synthesis. Main thing. So clock transition should be in the limit. For that reason only. So the clock transition will be in the limit if I reduce the load on what? Clock port. And if you reduce the load on buffers, the transition will be in the limit. And if I don't create long nets, the transition will be in the limit. Along with that, what is the constraint here? Insertion delay should be less. Insertion delay means this buffer delay should be less. It should not be very huge. That is a goal of CTS. Build a clock tree with less insertion delay. And skew. What is skew? See, for this flip-flop, the clock is reaching after 0.4 nanosecond. For this flip-flop, the clock is reaching after 0.2 nanosecond. What is the difference in time? So here the clock is reaching 0.1 nanosecond, 0.2 nanosecond early, right? Here clock edge is reaching after 0.2 nanosecond late, because here it is reaching at 0.2 nanosecond, here it is reaching at 0.4 nanosecond. This is called as skew. See, clock edges to all the flip-flops to reach at same time. That's the requirement. But because of this buffer delay, here I am getting the clock edge after 0.2 nanosecond. Here I am getting after 0.4 nanosecond. What is the difference in delay? 0.2 nanosecond. This is called a skew. This skew should be less. If skew is not less, this will lead to setup and hold violation. This may lead to setup or hold violations. Right? So what is clock tree? Build a clock tree by using what? Inverters and buffers. So goal of CTS is, right? Goal of CTS is meet transition time of clock. Meet transition time of clock. So you have to meet that. So next is reduce. Right? What we have to reduce? Reduce insertion delay. If insertion delay is more, it may lead to skew, setup and hold violation, or it may lead to more power consumption also. So that may lead to some other effects again, jitter, some other effects. So reduce insertion delay. So again you have to reduce skew also. Right? So reduce the skew. So if skew is not reduced, what is skew? Difference in delay between clock reaching to the clock pins of different flip-flops. So reduce skew. So we have to take care. This is reduced, right? All these things are reduced. So we have to plan a clock tree like this. So what is next? Next is routing. So now all cells are right. All cells are placed in the design core area, but they are not connected. So connect all cells, by using metal layers. Connect all cells, macros, right? Not only cells, macros, ports, by using what? By using metal layers. That is called as routing. So while connecting the metal layers, right, even few metal layers get shorted. If I don't get a sufficient tracks, even few metal layers get short. What? For example, I want to connect this cell, right, to this cell. I'm connecting, right. So here I am connecting to this cell to this cell. Even that both metal layers get short. Right? Sometimes if I'm connecting from somewhere from here to here, so I may get short here if I don't get sufficient tracks. So I should connect the cells without what? Shorts. We have to do the connection without shorts. And following the DRC rules, there are some DRC rules specified from the foundry in the TF file, technology file. DRC rules means between one metal layer to another metal layer, you should be having minimum spacing. Right? This is called as what? This is called as minimum spacing. If spacing reduces less than this, then that is a DRC rule violated. So minimum metal width, there should be minimum metal width for a metal layer. Minimum area for any object to be fabricated, minimum you should be having this much area. If the area is less than that, that object cannot be fabricated. So you have rules like this: minimum spacing, minimum width, minimum area. So you should not see shorts. So you have to route by considering all the aspects. Right? So routing should be done without DRC violations and without shorts. Routing should be done without DRC violations, without shorts. That is called as routing. So that is what, right? Checks after routing. What checks you do after routing? Main checks. See, we do all these checks again, right? Setup violation, hold violation. But main checks are you do DRC check, metal level DRC check. You are going to perform what? DRC check. DRC stands for what? Design rule check. Design rule check. So here we check for minimum spacing, minimum width between metal layers. Right. Here we check for minimum spacing, minimum width, minimum area. Right. No shorts. So even antenna effect. Is there any antenna effect? All these checks we do in DRC. These are all the rules specified in the file, right? TF file. So antenna effect is mentioned in foundry runset file. So by using this, all these checks will do. If all these checks are passed, then your routing is clean. So what is routing? Routing is nothing but connecting all the cells by using what? Metal layers. Like using metal layers, right? You will connect all the cells. Like this. Even macros also. And even you will connect output of these two what's output of these two ports also. Right? So next is LVS check. You perform LVS check. LVS stands for what? Layout. What's the schematic? So here, what is layout? What is layout? Layout is nothing but whatever we have, right? This is called as what? Layout. Here we have placed layout of a cells and how these cells are connected. This is called as what? Layout. What is schematic? Schematic is a netlist. Netlist is what? Schematic, not the initial netlist, what we use after synthesis. See, every time a netlist is updated. See, in routing stage, if you see in the CTS stage, you added few cells. Those cells are updated in the netlist. Tool will update everything in the netlist. For CTS stage, right, during placement stage, you added few cells to split the fan out. You add few cells. So even those cells are incorporated in the netlist. So DFT team, they added scan chain information. Even those cells, those information is added in the netlist. So updated netlist, right? The updated netlist we have during routing stage. So layout of schematic means check all connections. This mainly checks all connections in routed netlist, and layout. For example, in the netlist, right? You see in the netlist, what is the connection you are seeing here in the netlist? The output of AND gate is connecting to what input for your inverter, right? Output of AND gate with name what U1 is connecting to input of what U2. Whether the same connection is maintained in your design or not. For example, this is your U1. This is your U1. What is it? This is your U2. So between U1 and U2, you have same connection or not in the layout. For example, connection is not there between U1 and U2. Then my tool will report as an open net. Open means connection is not happened between U1 and U2, but connection is present in the net list, but not present in the layout. Here there should be a metal layer, right? Between U1 and U2, there should be a metal layer. Connection should be there, but that connection is not there. Then this is called as what? Open net. And for example, there is a connection between U1 and U2, right? And one more metal layer is passing here. There is a short here. So in the netlist, there is only connection between U1 and U2, but in the layout, if I see, this net is also connecting to what? Connecting to another cell, because the short is happened here. Two metal layers are they are shorted like this. So this information is not present in the netlist, but the short is present in layout. This is called a short violation. So layout versus schematic will verify what are the connections present in routed netlist and what layout. So it will report opens and shorts. It reports opens and shorts. Apart from this, right, you should do all the rest checks. Check match plans, match tab, setup violation, hold violation. Only 6 should do along with this. So if everything is clean, right, then you send your DB in the GDS format or in the def format or in the netlist format to sign off checks. What are different formats? Output formats. Output formats. So one is what? One is GDS format. Entire design you can write out in form of what? GDS, graphical data stream. Graphical data stream. So GDS format. So GDS has a complete layout information. So I told there is a file called as LEF file, right? LEF file doesn't have complete layout information. It's having only the layout, the layers which is required for PD. LEF has only the layers out of these layers, right? What PD wants? PD wants metal layer information, correct? Because the metal layer, what I'm routing, I should not start with internal metal layers. It wants metal layer information. It wants NVL to maintain NVL continuity to NVL information. Sometimes it requires polysilicon information. Apart from that, this P plus region, N plus region are not required. Then why I should load to the tool, right? If I load the regions to the tool, P plus region, N plus region, only the memory will get increased. So remove all these layers, only load the required layers. When physical design is complete, because anyhow I'm not going to test this base layers during PD. Well, physical design, I'm not going to test this base layers. When I'm not going to touch, then why I have to use this? So memory of the tool increases, runtime increases. So to avoid that, what we do is only we use what are all the layers required for PD. That layers only we use here. That is present in LEF file. So LEF we call it as a abstract layout information, not complete layout information. So in GDS, what we do is GDS is called as complete layout information. All cells we replace by complete layout information. The size remains same. Cell size will not change. Cell size remains same. Only instead of using all layout information, we use only abstract layout information. That is present in LEF file. Complete layout information is present in what? GDS file. So after doing all this design for entire design, you write out the GDS. But GDS in the compiled form. Human cannot read it. So it has complete layout information. So this design you can give to the physical verification team, PVT. So one more format is a def format, design exchange format. So entire design you can also write in what format? Design exchange format. But design exchange format in turn it will not be having complete layout information. Design exchange format will not be having what? Complete layout information. Only it is having abstract layout information. But entire design, right? Entire design, if you want to convert into one format means, then you can convert into what format? Design exchange format. So this design exchange format you can send it to timing sign off and power sign off team to verify timing and power. So all this is the steps in physical design. That is floor planning, placement, CTS, routing. After that, you extract the design in GDSR, def format. You send for sign off checks. So all this physical design is done in a tool called as ICC2. We use ICC2 for this. Yes, so the session is recorded. You can ask the admin, right? They will share you the session, the video. It is all the things we do in what tool? ICC2, integrated circuit compiler. So after doing all the steps and validating all the checks, then we can dump the design in GDS form and def form, and we can send for different teams. One more format is a netlist. So what is the difference between a def and netlist then? It's a very important question. What is the difference between def and netlist? See, netlist has like this, right? Netlist has like this is the netlist. It has cell where this cell is present in the core area. We don't have location information. So inside this core area and get where it is present. Right? I don't have this information, right? By using netlist, I cannot create this physical design. Suddenly, by loading, if I load the netlist, this physical design will not be created. Again, I have to start from one step, right? Do floor planning, placement, everything. Netlist has the cells and the connection between the cells. That's it. But where this cell is present, where port is present, what is the distance between core area and die area? So core area and die area, what are the coordinates? All this information is not present in the netlist. But in the def file, along with the cells, its connections, we also have coordinates where it is present. For example, this cell is present at what coordinate? This coordinate LLX, LLX, LLY means lower left coordinate information, upper right coordinate information that is present for each and every cell. So if I load the def, automatically I can create this physical layout view because my tool knows, right? In the def format, I have okay core area, lower left coordinate is this much, right? Upper right coordinate is here. So then connect it from the core area by connecting the lower left coordinate and what upper right coordinate. But coordinates is present in what? Def file. But the coordinates information is not present in the. Okay, I have a cell. This cell is present. This is a lower left coordinate. This is a upper right coordinate. Okay, then place this cell upper. Start from upper right coordinate until lower left coordinate. Place the cell. Place a cell like this. So if I have coordinates information, I can create the entire physical design view in whichever tool I'm using, and I can create it. But by using netlist, I cannot do that. Correct? So that is the difference between def format and netlist. So def has coordinates, but netlist has only cells and its connections. That's it. It's having cells and its connection. That is what the netlist has. So first we start with generally we start with the power sign. Generally we start with what? Directly we not go with timing sign off. We start with what? Power sign off. For power sign off, right? Power I can tell power or IR drop sign off. IR drop. Analyze IR drop. Whether all cells are getting the same voltage, 1.5 volts. Whether there is a voltage drop. If voltage drop is there, where the voltage drop is happening. Analyze that. So for this, we use a separate tool called as a radar tool. In Synopsys, we use separate tool called as radar tool. In Cadence, they may use some voltage tool to do that. Radar tool is used to analyze IR drop, power consumption, etc. IR drop and power consumption. And even they may give the solution also what you should do to fix the violations. like increase the strap width or use more straps or insert decapsules. Even they will provide the solutions if there is a more IR drop. So next is a timing sign off. Timing sign off. We use prime time. Prime time tool is used in Synopsys and Tempus is used from Innovus or from Cadence. Innovus is used from Cadence for timing sign off. So to analyze setup and hold violations. To analyze. See, setup and hold violations are major checks. Apart from that, we also check max cap, max transition, crosstalk glitch, right? Even power recovery is done. So plenty of the things are there. See, I am telling only a major things. See, in-depth concept we'll see in the later stages. Only I'm telling the major checks. So major checks here is a setup and hold violations. So if I want to tell about in depth of prime time means it will do max capacitance, max transition, min capacitance, pulse width violation, duty cycle distortion, and crosstalk noise, crosstalk delay. So all these effects are verified in prime time. And after verifying, we also suggest what is the solution for this, how to fix if there is a violation. So all these fixing methods have to communicate back to the implementation team. These are the sign off teams. Sign off teams will also communicate to what again? Implementation team. Again, they have to incorporate all these changes, whatever the suggestions given from sign off team. That is called as ECO. So, for example, my timing sign off team tells that insert buffer in few places. I have to insert buffer in few places, and for those few buffers, I have to reroute it. I have to do what? Rerouting. So that is called as ECO, engineering change order. In ECO means implementing the changes or solutions given from such sign off teams. Implementing in our design. Implement that. Again, you send back the DB. Right? So DB means in GDS format you give to physical verification team. In def format and netlist format you give to what? Power and timing sign off team. So last is, what is last thing? Physical verification. So it performs DRC and LVS checks. Same, whatever you have done earlier, they will also do your DRC and LVS checks. In ICC2, we can do only base level DRC check. Sorry, metal level DRC check. Even base level also they have to check. Base level means, see, if you see this layout, right? Metal level means only metal layers. Checks we do. Base level means like N well, P plus region, N plus region, active regions, polysilicon. These are called as what? Base level. So even base level DRC check is done by what? Physical verification team. So they do both the metal layer and base level DRC checks. Both base level and metal level DRC checks. So any changes, they will communicate us back. For example, they have found that tap cell placement is not sufficient and there is a placement of end cap cells, there is a problem. They'll communicate back to us. So in this region, tap cell placement is not good. So everything they'll communicate us back. The solutions, what we have to do. Right? So if everything is clean, then the block level can be sent for integration. The chip top will take care about integration of block level. Or full chip level designer will take care about the integration of block level design. So this is about your physical design. What you did in physical design, whatever the gate level information you got in synthesis stage, you placed what for the gate level information, you placed what layout level cells and you connected them, right? But connection you cannot do blindly. You should see that there is no shorts because you're handling millions of cells or thousands of cells. There should be no shorts, no DRC violation. Your timing is met, and you're using minimum area. Right? This should be your main focus. Timing means there should be no setup and hold violations. That is called as timing. So this is what called as physical design is, right? So to implement this physical design, so what basics you want? Basics are required to start with this course, right? What basics you want? So you should be compulsory knowing your digital. Digital you should be knowing compulsory because if I tell asynchronous reset flip flop, you should be understanding what is meaning of asynchronous reset flip flop. If I tell synchronous reset flip flop, you should be understanding what is the meaning of synchronous reset flip flop. If I tell decoder, you should be knowing what is meaning of decoder at least. If I talk about setup and hold violations, so you should be knowing how D flip flop is implemented internally. What are the digital circuits used to implement D flip flop? So you should be knowing your digital completely. If you know your digital, then you can understand the terms what we are talking, right? So what is meaning of asynchronous reset? Yes, to affect the value of reset, we don't want clock edge. Alright. What is the difference between latch and flip flop? Latch is level triggered, flip flop is edge triggered. So like that, you should be knowing the digital properly. Then only we can do static timing analysis properly, or else it is very difficult to do. Then after digital, right, you should be knowing about Unix. What is Unix? User commands which is supported by Unix operating system. The commands which the user can use to interact with operating system. So Unix will make interacting with the operating system very easy. For example, here if I want to create 10 folders, right? What I should do, right click a new folder, change the folder name. Right click a new folder, change the folder name. But same thing if I want to do in Unix means I can simply use the command mkdir, right? Like folder name, right? F1 folder names you give. F1 is one folder name, F2, F3, F4, F5, F6, F7, F8, F9. 10 folders are created. So there are plenty of advantages when you learn Unix. It is a commands by which we can interact with operating system. If you want to go from one folder to another folder, what you do in Windows? Double click, right? Double click on the folder, you'll go inside the one folder. There you can press what CD folder name. The command if you use CD stands for change directory and folder name. You enter into one folder. First method. Second thing is it is faster also. If instead of using GUI, if I use a command, it's faster to operate. See, I have a folder here. Right? I have a folder. For example, I have few files. Few files are starting with name PD. Few files are starting with name STA. Few files are starting with name functional verification. Few files I am having starting with name something, right? If I want to get only file names which are starting with the PD, then easily I can do it by using commands. All those file names I can copy and paste, everything I can do. Here copying and pasting is very difficult. I want to copy all the file names, I'm telling you, not the files. Copy the file names. If I want to copy file names, what I should do? Here. Yeah, I should go to rename and I should copy, right? Control C. They're copying the file names are very easy that we can use for some other purpose. So for that purpose, you need what? Unix, complete Unix knowledge you should be having. If you know Unix, you can handle the operate. Next is third thing, you should be knowing TCL, TCL basics, tool command language. ICC2 or Innova's tool that is used to implement PD can understand this language, a tool command language. So if we want to interact with the tool, then we should be knowing what a TCL, tool command language. So you should be knowing complete TCL basics. So next is CMOS basics. So even we can do many things automated also by using tool command language. The things which you can do, one for example, I have 1000 violations and I have a method to fix it. To fix 1000 violations, I should do one by one, right? Take first violation, fix it. Second violation, fix it. Third violation, fix it. Instead of doing one by one, to reduce the human effort, we can write the program to fix all the violations. 1000 violations by using what tool command language. If I source the file, all the violations will be fixed. So TCL is very important language for physical design. You will grow very well if you know TCL in the industry. If you know how to make the things automated, then you will go very fast. And if you know TCL very well, your efforts also is reduced. See, TCL program you will not write for every program, every different designs, right? Once you write and keep the TCL program, for every design you can use the same programs to fix the violations. You need to put all the efforts for fixing. So after this TCL basics, very important is CMOS basics. Now I ask the question, what is CMOS inverter? How to implement AND gate by using CMOS logic? How to implement NAND gate by using CMOS logic? What is IC fabrication steps? So what do you mean by P-type semiconductor? What do you mean by N-type semiconductor? Inside CMOS, what are all the layers present? Like you have P substrate. If I take N MOSFET, you have P substrate. You have source and drain made up of N-type semiconductor. You have polysilicon as gate and you have silicon dioxide in between. How to write the layout? Layout you are not going to draw. There is a separate team. But at least you should be having the knowledge of what? Layout. For at least few cells like AND gate, NAND gate, and NOR gate, how to write the layout. So these informations you should be knowing. CMOS basics is very important. So these four topics is required to go with what? Physical design. Digital basics, Unix basics, TCL basics, and CMOS basics. So this covers as, see, we have two things here. One is a basic part. One is advanced part. So basics we take almost 2 to 2.5 months to complete, and advanced will take again right 3 months to complete. So total it is of right? So 3 to 3.5 months. Total it is of 6 months training, including basics. Excluding basics, it is only if you take advanced part. It is, see, if you take advanced part, you should be knowing all these things. Then you can take advanced part. It is how much? 3.5 to 4 months of training. Right. So now training goes on like this. So basics, it is like weekdays and weekends. Daily 1 day, weekly is 1 day holiday. So daily 3 hours of sessions for basics. Basics, daily 3 hours of session. Starting from same order, whatever the order I have mentioned in same order, the classes will go on daily 3 hours of sessions. All the days except 1 day, week off. Probably it is on Sunday. Probably. Sometimes if trainer is not available on Sunday, he may take some other day and Sunday will be the class. They'll intimate you. So this daily 3 hours of sessions. And when we come to advanced part, so advanced part is like this, right? Weekend means what? Weekend, that is a Saturday and Sunday theory, because industry experts are available only on Saturday and Sunday. So Saturday and Sunday they handle what? Theory. Theory means they not only do the theory, they'll do even the lab part, even they'll show the lab part also. But you cannot do along with them. If you want to do along with them in entire 3 hours, they will command. They will do only one command, because you are in the starting stage, right? So they will do theory, that is for 3 hours, Saturday and Sunday. So weekdays you have lab. What is done in weekend, right? That they will do it in so slow phase, so that even you people also doing along with us. So the trainer will be there even for weekdays. So weekdays, right, from Monday to Thursday. Monday to Thursday, lab. You have lab for that. So even the persons, if they are working, right? If any persons are working, if they can attend weekdays lab, even lab is there for weekend lab is also there. Weekend lab, totally different. Weekdays lab is different. Weekend lab is different. This weekend lab is for the persons who are working during weekdays. They are working in some other companies and they can attend weekdays lab. Then for them, we also have weekend labs. Only Saturday and Sunday we do lab after the theory session for them. That depends upon how many of them are enrolling like that. If they request for a weekend lab, we are also conducting weekend. Right. So we have periodic evaluation, right? Periodic tests are there. Periodic evaluation by test. Periodic evaluation you have, test you have periodically. Periodic mock interviews means mock interviews. What are the questions, expected questions from the industry will be asked to the students? Periodic mock interviews. If you perform very good in this, right, you will be considered for placements. If you perform good. See, because if you perform good, then only the company will take. Or else company will not take. If you tell like I have done my course in so and so institute, no company will take. The company will take only if you perform well in the mock interviews. Then only the company will take. So for that purpose, we will be doing periodic evaluation and periodic interviews. It's not that we are going to do only in the last. For example, after completion of digital, we can do one test. After completion of Unix, we'll do test. After completion of TCL, we'll do test. After completion of CMOS basics, we may do test and mock interviews. Topics based on CMOS, like what is BJT, why it is called as a bipolar junction transistor. Already it will be covered in CMOS basics. Why it is called as a bipolar junction transistor? What is MOSFET? What is the difference between MOSFET and JFET? This is not done in PD, but still they may ask in interviews to test your basic knowledge, how much you have. So periodic evaluation and periodic interviews, mock interviews will be done, right, from the experts to evaluate. See, it is not only to evaluate, to give you the feedback. So you have to improve in this concept. You have to improve in communication. You have to improve in the technical concept regarding to STA. To give you the feedback also, we are conducting this. Right. So this is about your course. So if you have any doubts, you can ask me. Technical doubts you can ask with me. And this, right, if you have any doubts regarding, right, if you have any doubts regarding the fees and placements, right, you can ask with manager. So Vaibhav is a manager, right? His phone number is this one. You can discuss it with manager regarding the fees and placement things. Right? You can discuss with him. You can call to this number and you can discuss with them. Or you can drop even a WhatsApp message, whatever information you want. So if you have any technical queries, you can discuss with me. You can ask me now only. It is done. No, done. Will you come now? Yes, Vaibhav, sorry. Manager will be correcting with you people. He'll be joining in 2 minutes. See, if you are enrolling to the course, right, the further information institute will communicate with you. If you are enrolling for the course, they will create a WhatsApp group. In WhatsApp group, everything they will communicate. At what time the class starts. So when the class begins, everything they will tell you, right? So they will inform you. Just 2 minutes, manager will join to the meeting. Any queries you can ask with the manager. So even technical doubts, if you have anything, you can address in the group itself. So they will connect with me. I will answer to them.
Yeah. Good afternoon, everyone. Myself, Vaibhav. I am the manager of VLSI Group. Basically, I will be looking into training and the placements. Training and the placements indicates. So basically, Deepak has provided you all the details about the course structure, how the course will go, right? Once I will just glance you about how what will be the training structure and how the training will go. So basically, as discussed, it will be around 6 to 7 months of course, that is 6.5 months we can consider. During this 6.5 months, we will be taking multiple modules. This VLSI design flow, digital design, Linux. These are nothing but the modules where we will be teaching you starting from the scratch. Like take an example of digital design. I will start it from AND gate, OR gate, one's complement, two's complements, that to even Boolean expressions, conversions. Everything will be starting from the scratch. Okay, that's the reason of spending dedicated around 2 months to build up your basics, to make you expertise in the basics. Once you are strong with the basics, then we will start with the projects. What does that project indicates? It starts with the synthesis, timing constraints, placements, initial design setups, even NDM libraries. Here what we will be doing is the two projects will be involved. One is on 14 nanometer and another project will be on 28 nanometer. Now, for us to explain these topics like synthesis, timing constraints with some small examples, it will hardly take 1 month. Still, why we spend almost 4 months? Because whatever projects we are doing, in both the projects, this synthesis will be implemented, timing constraints will be implemented, each and everything will be implemented, and few topics will be given as assignments. Now, what do I mean by assignment? It doesn't mean that we just give you the assignments you have to do. The structure is divided in such a way that if you are enrolling for a full week training, there will be 2 days theory, 4 days labs. What happens in the theory? The trainer will teach you around 5 to 6 topics per day over the tool. Every session that we are doing in this 6 month time span, initial 15 minutes, he will invoke the tool, he will log in into the tool, and everything he will be demonstrating onto the tool itself. Now, in theory session, he will teach you, but in the lab session, under the guidance of the mentor, you have to do the hands-on. And while doing the hands-on, if you are stuck at any point, offline candidates can come to the mentor, or even online candidates can share their screen. The mentor will help you debug. Because if, let's take an example, 6 days a week I'm doing training, 40% will be learning and 60% will be on hands-on. That is the reason company considers VLSI Guru profiles compared to the other institute. So every topic it will be a complete hands-on over the tools. Coming to the tools, now for different process, like for example synthesis, STA, we require prime time tool. For floor plan, we require ICC2 tool. So a complete set of synopsis tools, that is ICC2, prime time, star IC, Red Hat. The access will be 24/7. We will create a VPN credentials to log in into the server, and through server you can access the tool 24/7. That is one. So let me note down the topics in a sequential manner. Romans basics. Okay. Now, if I'm not wrong, majority of the people are joining with a perspective to get into industry. Am I right? Right? Your perspective is to get into the industry. Now, what is the requirement of the industry, or what is the requirement of the company? Online candidates. Yeah, I expect all of you to be responsive during the session so that I will understand your requirements as well. So online also, like Shweta, Abhishek, Balaji, Divya, Kirti, majority of the candidates are joining with the perspective of placements and to start a career into VLSI. So we need to understand that what is the expectation of the companies. For example, if a company comes to VLSI Guru Institute, they will be expecting trained candidates or the expertise candidate. Like if a candidate has the expertise, they will hire. Providing you that expertise, providing you that tool access and everything, and providing you that training is the role of VLSI Guru Institute. Now, one more example I will give you. The trainers that we have are industry professionals working as the team leads in product-based companies like Qualcomm, Intel, Synopsys. Okay. They will be teaching you all the projects, all the topics. But is it possible for them to provide you all the interview questions? Is it possible online? Yeah. Kirti, Nilima, Rahul. Okay. So coming to this, the question about, is it possible for the trainer to share all interview questions? The answer is no, because he had to teach the topics, he had to do the hands-on, he has to demonstrate you. So for that reason, what we have done is we have our in-skill portal. Yeah. So once you enroll for the course, you will be getting the login credentials of this portal. As of now, I will be entering mine. So see, if you enroll for this physical design, this tab will be open for you. And when you go into this tab, you will be able to see all the session recordings are available. there are the slots, or I can say separations like video, schedule, presentations, assignments, notes. So what happens is now when the demo session is going on, Deepak has made the notes in the notepad file, right? He has given you all the details, and at the time of joining the session itself, you might have heard that this session is now being recorded. What happens is, even if you are attending offline or online, the session that we are doing, it's getting recorded in the background. So what is our expectation, even if you are online or offline? When you are in the session, you have to learn the things, clarify the doubts. Because once the session is done, then within couple of hours, the same session will be uploaded onto your portal. Now the sessions that you are seeing over here, that is unit 1, unit 2, these are nothing but the live sessions recording. So whatever I am teaching live to the offline candidates, the same is shared to the online candidates also. So you should not be having a question that what if I get disconnected in between? Like suppose you are attending online but you get disconnected. Still the entire session will be available for you, and this live session recordings will be available for 10 days. Like suppose today I'm doing the session, it will be available for 10 days. So that after the session is done, you can watch the video multiple times and you can make the notes. Now how will I come to know? Coming to the placements, how will I come to know that this candidate, suppose there is a batch of 25 candidates, how we will do the separation that these are performing candidates, these are not performing. Even if the candidates are not performing, what we do is we provide additional supporting sessions to check where they are lagging, and those supporting sessions will map them up with the same level where the performing candidates are. Now, the question about placements, how will I come to know the candidates are performing? So, as I was going through the syllabus, after completion of every module, after completion of every module, there will be a evaluation. Like digital is done, there will be evaluation. After that Linux is done, then there will be evaluation including digital and Linux, then TCL scripting. So periodic evaluations will be done. Along with that, we have seen that there are people who are facing some issues with the communication. They are not able to speak up, or they are not able to represent themselves. So we have the soft skill training also, which will be happening weekly twice. So evaluation will be the first step of evaluating the candidate to check the performance. Non-performing candidates will be provided additional support so that they will ramp up with whatever topics they are lagging. Second thing is, once they are clearing the evaluation, we will start conducting the mock interviews. So basically, when it comes to the companies, majority of the companies will be having 4 rounds of interview. First is written test, which includes the basics. Second is the HR round. HR will just ask your communication basic information. Then there will be a technical discussions. In the technical discussions, majorly the questions are asked related to the project. The basic questions that they ask in the related to the project, okay, what projects you work, what problems you faced in the project, and how you overcome it. That kind of questions will be asked. For that reason, we will having mock interviews, that too with industry professionals. So having mock interviews and all increases your chances to get placed. That too also, if you are not able to clear, what will happen is, see the possibility that you get into first company and you get selected. There is no 100% chances, right? You might have to go for 2 to 3 companies and then you will get selected. How we are going to support you is, in first company, if you are getting rejected, we will provide a supporting sessions of where you got rejected. Are you not able to represent the project, or you are not able to understand the questions asked in the project? In that context, after every interview, we will support. In that context, till you get a job, we will forward your profile and then we will keep on supporting. Till here, any queries? Yeah. One more thing, once the candidate, see, suppose out of 25 candidates, 5 people are coming and saying, sir, I'm very well prepared, please give me the placement. How can I come to know that yes, he is very well prepared? Or else 25 people can also come and say that we are well prepared. Someone saying well prepared doesn't give me any clarity. But someone comes and says, sir, I am done with 70% of the assignments, gives me the very clarity. Why? Because the assignment questions are nothing but the interview questions. So if you are prepared with the interview questions, if you are done with the assignments, definitely you are well prepared to sit for the interviews. Now coming to the schedule, We will be having 2 batches. Full week batch, the training will be 6 days per week. 30 to 1:30. For weekends, it will be on Saturday, Sunday. Theory sessions will be in first half, that is 9:30 1:30, and the lab sessions will be at 2:30 to 6:30. Now, we provide you the flexibility of, see, there will be a common WhatsApp group for online and offline. Today you are coming online, sorry, today you are coming offline, tomorrow you are attending online, or even you are not attending online, offline, but you are going through the videos. We are okay with everything. We are not here to monitor that how you are doing. The only thing is, in the evaluation, your performance should be seen. I am not restricting that you have to attend online. Online candidate should attend online only. Offline should be online. There are no access restrictions. But at the end, the performance should be seen, because that is the reason you have joined the institute, right? Yeah. Any questions apart from this? Yeah. So online students, please put your queries in the chat box. One by one, I will address. Yeah, so there was one of the question, how e-learning is different from online mode. See, in e-learning, since we have conducted previous batches also, that previous batch videos will be provided by module, and after completion of every module, there will be evaluation. Based on that, we will provide you the other module success, and once you complete, then we will conduct mock interviews. If you perform well in the mock interview, same placement protocol will be followed up, forwarding the profiles to the company and providing additional support till you get a job. E-learning is mostly for those who are working and they don't have Saturday off also. Those who are already working, for example, into IT domain or even teaching domain, they can opt for e-learning. And even if they have Sunday off, what happens in e-learning is a dedicated mentor is allotted, where not even in e-learning, in all modes of training, a dedicated mentor is allotted. In e-learning, as per the flexibility, you can have a doubt clarification session with the mentor and proceed again. Like, for example, you've gone through 2 to 3 videos and you have any queries, you can directly ping to the mentor. The next day session will be arranged and the doubts will be clarified, so that you can move to the next videos. The 2 lectures and the lab videos will be also shared, because each and every each and every sessions are getting recorded. Any other queries? So basically, we are full week batch. Yeah, full week batch will be from for the basics. The batch will be Monday to Saturday. Once the basics is done, it will be Monday to Thursday. Friday will be off. Then again Saturday, Sunday. Offline candidates, any queries? Okay, fine. None news. So from tomorrow we are starting a batch, and the enrollments are open till Wednesday. In case if you have any queries, you can let me know. Okay. Apart from this session also, if you have any queries, you can get back to me on this number, that is so. Apart from this session also, you can get back to me on this number, or else you can mail me also. See, now enroll candidates will be added into the group. Once you enroll, you will be also added into the group. I will be in a touch till your placement. For example, the group is created, but there is a delay in the response, and you are facing any delay in any kind of like scheduling and all, you can directly get back to me on the number that I have shared. My team will be responding. Any other queries? Online candidates? Yes, you can shift between full week to weekends anytime as per your convenience. For e-learning, the 10 days time restriction won't be applicable because the access will be provided module by module. Like for example, TCL scripting, the access will be for 1 month. So for 1 month, the videos will be available. Any online candidates, any other queries? So I will share my contact details in the chat box as well. Anytime, any queries you have, you can get back to me. The batch is starting from tomorrow till Wednesday. You can confirm your enroll. Regarding the fees and all, please get back to me on WhatsApp or mail. I will revert all the details. So by this, we will end the session here. Thank you, everyone. Yeah. So Kirti, since you are taking online session, yes, you can switch to hybrid mode. The fees is same for the hybrid mode also, online and the hybrid mode as well. Yeah. Please revert on the contact number for any other queries. Yes, you can take a gap between the main course and the basic course. Whatever, if you think that you want some time or you're occupied with the projects, definitely you can take a gap and then again start. We are starting a batch every after 6 weeks. Any other queries? Yes, even if for online live training, access to the recorded videos, every live session video will be for 10 days. If you're going for e-learning, that previous batch videos will be provided on a module by module basis. Now, even this session that we have conducted, these session recordings will be also shared to your registered mail IDs. Within couple of hours, it will be shared. Mostly before 5 o'clock, it will be shared. Okay, sure. Thank you.